Hello and welcome to my channel, ELECTRO-MASTER. Today we'll talk about the contactor, an electromagnetic switch used to start or stop large industrial equipment like motors or lighting systems. How does it work? A contactor has an electromagnetic coil that, when powered, creates a magnetic field that activates a movable metal core to control the contacts. There are power contacts that allow current to flow to the load and auxiliary contacts that send signals to other devices. Contactors come in various sizes and voltages, ranging from 24V to 230V, and are essential for safely and efficiently controlling large electrical circuits. I will start by demonstrating how to operate a contactor using two buttons. The green button, this is the start button and features a normally open, NO, contact. When pressed, the contact closes, allowing current to flow, energizing the contactor's coil, and activating the power circuit. The red button, this is the stop button and uses a normally closed, NC, contact. In its normal state, the contact allows current to pass, maintaining power to the coil. When the button is pressed, the contact opens, cutting power to the coil and stopping the contactor. This combination of buttons provides a simple and effective method for controlling the start and stop functions of a contactor in electrical circuits. The contactor's coil in this case is powered through terminals A1 and A2 with a voltage of 230 volts AC. I will begin by connecting terminal A1 of the coil in series with the normally open contact of the green start button and the normally closed contact of the red stop button. In this setup, I will use the brown conductor for the phase circuit and the blue conductor for the neutral circuit. This color coding ensures clear identification and proper wiring, aligning with standard electrical practices for safety and functionality. Control buttons are essential in any electrical system, providing the user with the ability to control various equipment by pressing them. There are several types of buttons, each with characteristics that make them suitable for different applications. One of the most common types is the mechanically retained button, which stays in the pressed position once activated, and only an additional action can return it to its initial state. These buttons are used in situations where it is desired to keep a circuit active, such as starting a motor or an electrical system that must remain on until manually stopped again. On the other hand, there are non-retaining buttons, which are typically used for temporary actions. When pressed, they complete the circuit, and once released, the contacts open, and the circuit automatically stops. These are ideal for a start-stop functions that do not require the active state to be maintained for long periods. There are also electrically retained buttons, which use an internal switching system to keep the button in its state without requiring continuous pressing. In this case, we will use non-retaining buttons, which allow the circuit to be activated only while the button is pressed, and when released, the connection is automatically interrupted. This is a simple and safe way to control electrical equipment. I connect the phase conductor, which supplies 230V power, to the normally closed contact of the stop button. This ensures that when the stop button is pressed, the circuit is broken and the current flow is interrupted, stopping the operation of the contactor and the connected load. When the stop button is not pressed, the circuit remains closed, allowing the current to flow through the system. I will connect the blue conductor, which represents the neutral, to terminal A2 of the contactor. This will complete the circuit, allowing current to flow properly and activate the contactor coil when supplied with voltage. This ensures the correct operation of the circuit. The contactor remains activated as long as I keep the green start button pressed. When the button is pressed, current flows through the contactor's coil, creating a magnetic field that attracts the contacts and keeps them closed. This allows current to pass through to the circuit it controls. Once I release the green button, the circuit is interrupted, and the contactor returns to its resting position, stopping the current flow. The self-holding of a contactor is achieved by using an auxiliary contact of the normally open, NO, type mounted on the contactor. When the start button is pressed, the main contact of the contactor closes, and the coil is powered, thus activating the contactor. At the same time, the auxiliary contact of the normally open type closes, completing a self-holding auxiliary circuit. Therefore, even if the start button is released, the auxiliary circuit remains closed, keeping the coil powered and the contactor activated. This self-holding circuit is essential in many applications as it allows the contactor to remain active without the need to keep the start button pressed. The self-holding circuit remains active until intervention occurs in the stop circuit, by pressing the stop button, which opens the auxiliary contact and cuts off the power to the coil. The auxiliary normally open contact of the contactor will be connected in parallel with the normally open contact of the start button. This means that, when the start button is pressed, the main circuit closes, powering the contactor coil and activating it. At the same time, the normally open auxiliary contact will close, creating an auxiliary holding circuit. Thus, after the start button is released, the auxiliary contact remains closed, keeping the coil powered and the contactor activated. This arrangement ensures that the contactor remains operational even after releasing the start button, and the auxiliary contact will keep the circuit active until the stop button is pressed. Now the magic happens. As you can see, the contactor remains activated even after you release the start button. This is the result of the self-holding process, which uses the contactor's auxiliary contact. When the start button is pressed, the contactor is activated, and at the same time, the auxiliary contact closes, keeping the circuit powered even after the button is released. This simple but essential function is used in many electrical applications to ensure that equipment stays operational without the need for a constant button press. If you understand how this phenomenon works, you'll be well on your way to understanding other fundamental electrical principles, which will open many doors in the world of electricity. Next, I will show you how we can use the power contacts by connecting an incandescent bulb to a 230-volt supply. The power contacts are the main contacts of the contactor, used to control larger loads, such as light bulbs, motors, or other electrical equipment. For this example, we will connect the incandescent bulb to the power contacts of the contactor using a 230-volt circuit. When the contactor is activated, the power contacts close, allowing the current to pass through the bulb. As a result, the bulb will light up, demonstrating how the contactor can control a high-power load. This is a simple but effective example of using power contacts to control electrical equipment, and this principle can be applied in many industrial and automation applications. For those of you who haven't gotten bored so far, I will now show you how we can add a new feature to the circuit created earlier, namely the insertion of a time relay. A time relay is a device that allows for delaying an event or action over time. For example, we can use a time relay to delay the activation or deactivation of a circuit after the start or stop button has been pressed. In our circuit, we will insert the time relay so that when the start button is pressed, the contactor will remain activated, but a certain amount of time must pass before another circuit or function is activated. This can be useful for applications where we want to delay actions like turning on lights or starting equipment, providing a more complex and controlled functionality. Inserting a time relay can add an extra level of flexibility and control in electrical circuits, which is essential in many industrial or automation applications. Just as the contactor has A1 and A2 terminals for power supply, the timer relay also has the same A1 and A2 terminals. In this case, we will connect the power supply terminals of the timer relay in parallel with the power supply to the contactor's coil. So, when the start button is pressed, not only will the contactor coil be powered, but the timer relay will also receive the necessary voltage to begin functioning. However, unlike the contactor, which acts instantly, the timer relay will introduce a delay before the circuit reaches its final state, depending on its settings. The timer relay has two contacts, one normally closed, NC, and one normally open, NO. In this case, we will use the normally closed contact, which is labeled 15 and 16. When the timer relay receives power and starts functioning, the normally closed contact, 15 to 16, will remain closed for a period determined by the relay settings. After the preset time expires, this contact will open, interrupting the circuit. As mentioned earlier, the auxiliary holding contact of the contactor will be wired in series with the normally closed, 15 to 16, contact of the timer relay. Thus, when the start button is pressed, the contactor coil is powered, and the contactor is activated. At the same time, the auxiliary holding contact of the contactor closes, keeping the circuit active even after the start button is released. After the preset time expires, the timer relay contact, 15 to 16, opens, interrupting the auxiliary holding circuit of the contactor. This results in the interruption of the contactor coil's power, and the contactor deactivates. As a result, the entire circuit is deactivated, and the devices connected to the contactor's power contacts will no longer be powered. Thank you for watching the video. I hope you found it useful and that it helped you understand how contactors work in electrical circuits. In the next video, we'll dive into the world of inductive sensors and a radio frequency remote control device. If you enjoyed this content, don't forget to like, share your thoughts in the comments, and subscribe to stay updated with future tutorials. Thanks again for your support, and I'll see you in the next one.